one final example of being able to work with spherical coordinates. So an application, let's say we want to find the volume of the solid that lies within a sphere of radius 2 above the xy plane, and then finally it's going to be below a cone z equals x squared plus y squared under a root. So let's get an idea of what we're actually looking at here. All right, so now again, we're only above the xy plane, so remember xy plane is going to be z equals 0. So xy plane, z equals 0. So let's graph. So if I was to graph this, we have a sphere, although technically, because we're only worried about everything above the xy plane, we're going to get that. And then we have a cone that's inscribed within the sphere. And what we're looking for is we're looking for everything below the sphere. Okay, so all the volume that exists beneath. So I'm just going to draw that, and let's just draw our sphere. All right, so that's what we have. All right. So I think when we're looking at this, I think it's pretty clear that for the bounds for rho, we're going to go from 0 to 2. All right, and that's just because we can see up here that rho squared is equal to 4. That means that rho is going to be equal to 2. All right, so that's easy. All right. Another thing that I think is pretty easy is to see the bounds for theta. Notice that theta is going to go completely around. Okay, so we didn't bind it by an octant or anything like that. So theta is going to be equal to 2 pi. It's the entire sphere. So it doesn't say half the sphere, at least above the axis. So we're completely rotating it. The problem is what is this angle? What is phi in this case? That's the question. And to be able to find phi, we probably have to go through and figure out at what angle does the sphere as well as the cone intersect with one another. All right, so let's try to figure this out. All right, so some of the angle, in other words, we could try to figure out what this angle is right here. Okay, at least with the cone, and then maybe from there we can try to figure it out. Okay, so here's what we can do. We can say that z, recall that z is x squared plus y squared under the square root. And recall that we have the different definitions for z and x and y in spherical coordinates. Okay, so you'll probably recall, and I'm going to have to do this down here to be able to get some room, but z, remember, is rho cos of phi. Remember that x is rho sine phi cos theta, but we're going to square that. And remember that y is rho sine phi sine theta. And we're going to square that. And so we're going to have to do a little bit of algebra or a little bit of trigonometry to be able to solve this. All right, so rho cos phi is going to be equal to, now just bear with me, so rho square sine square phi cos square theta plus rho square sine square phi sine square theta. And what you probably notice is that there's a common factor of rho sine square phi that exists in both of those. So let's factor that out. And you're probably seeing some of the magic that's going to happen in this case. So we're going to get rho cos phi is equal to the square root of rho square sine square phi, and then we're left with cos square theta plus sine square theta. And of course we know that's our Pythagorean identity. So this sine square plus cos square of theta is 1. So we're getting pretty close to figuring out what phi might be, that angle. And most of you could probably see just by inspection what it's going to be. So now we get that rho cos phi. Let me back it up. I'll put it this doesn't have any significance. I try to utilize different colors for when something has significance. So rho cos phi is equal to the square root of rho square sine square phi. Or in other words, rho cos phi is equal to rho sine phi. Now we're trying to solve for phi. All right, so the good news is we don't necessarily care about rho. Let's divide by both sides by cosine. So we're going to get 1 is equal to sine phi over cos phi. We know that sine over cos is tangent. And then all we need to do is we need to figure out the angle at which the tangent of phi is equal to 1. And so we know that the tangent of pi fourths is equal to 1, which implies that phi has to be equal to pi fourths. So going all the way back up here, the angle right here for phi that's on the cone is pi fourths. Okay, so this angle right here is when phi is equal to pi fourths. And then at the bottom, right here, right, so if we think about like that wedge, if you would, at the bottom, remember from the previous problem, phi is pi halves. Right? So now we have a range for phi. So now we have all three of our variables. And the good news is the integral is not too difficult to evaluate. Okay, so we're going to go back. And our triple integral. So we're going to have theta from 0 to 2 pi. That's easy. Phi is going to go from, remember we just solved it, pi fourths. That was the hard part to get that part. And then also pi halves, which is going to be the ground, okay, or the base of the floor. And then remember we had that rho was 0 to 2. We had a sphere of radius 2. All right. All of these contribute to the constructs of what's in that above the xy plane, okay, and also bounded by the sphere as well as the cone. Don't forget we need rho square sine phi as a multiplier, all right, and the order that we have it is d rho, d phi, d theta. All right. At this point, we're pretty much done because everything is, all the bounds are constants. So let's just split it up into three separate factors of integrals, 0 to 2 pi. So 0 to 2 pi of d theta, and that's nice. Okay. We have that sine of phi, so we have pi fourths and pi halves of sine phi d phi. So we're going to have to do a little bit of trig, not much. And then finally, we get 0 to 2 of rho squared d rho. Okay, so all three of these are fairly easy. So we know the first one, we've seen that a few times. That's just 2 pi. Okay, over here, rho cubed over 3 from 0 to 2. I think everybody can see that just becomes 8/3 because we get 2 cubed over 3 minus 0 cubed over 3, which is 8/3. We're going to hold on to those because that's what we're going to have to multiply by at some point. Okay. And then finally, let's go ahead and do the trigonometry to be able to evaluate this last part. So give me 1 second so I can get a little bit more screen in here. Maybe not. All right. So I'll just hit enter a few times. Hold on to this. And everything's still down here. Okay. So we still have that integral. I'm just going to copy it back up here. So we have integral from pi fourths to pi halves. And we had sine phi d phi. Antiderivative of sine, negative cosine of phi from pi fourths to pi halves. Okay, that means we get minus cos of pi halves minus a minus cos of pi fourths. Okay, fortunately almost done. Cosine of pi halves, 0. The x value at pi halves is 0. Opposite of negative cos of pi fourths just becomes root 2 over 2. All right, so Now we recall everything that we had from before. Okay, so we go back down. Remember that we had a 2 pi, we had an 8/3, and now we have that root 2 over 2. So now we have 2 pi times root 2 over 2 times 8/3 from the row. And we're going to end up with 8 pi roots of 2 divided by 3. Okay, and that should be our complete volume for this. All right. So hopefully this helps out a little bit with respect to being able to work with these cylindrical coordinates as well as spherical coordinates. Not an easy topic. So I'd recommend going back, maybe watching the videos a couple times, trying some practice problems.